And I want to start by thanking the organizers for having me here. And as you can see, the topic of my set of classes is optical lattices. I am from the Federal University in Rio. And preparing this set of classes, I came to realize that this June we have celebrated 30 years of the first Bose-Einstein condensate that has led to the Nobel Prize in 2001 for these three gentlemen. And this started a field, I think, of cold atoms. Not started, but, crowned the beginning of this field of cold atoms. And in 30 years, really a lot has happened. So how do we go from a Bose-Einstein condensate in 95 and 30 years later, neutral atomic Hilbert model in the cryogenic limit, and I'll talk a lot about temperature, and this is really a big achievement that's going to be a game changer. So what happened in 30 years is obviously a lot to cover and impossible to cover, so choices had to be made. And I realized that in preparing these choices are deeply personal, so I made the choices, and if you had somebody else give this set of classes, another person would make completely different choices. So I am going to talk about things I find interesting, and this is in a way personal, but more than that, this is a very, very interdisciplinary field with people working on it from different fields on physics, optics, atomic and molecular field. There is a lot being done from people from quantum information and condensate matter. So I am a condensate matter physicist, and my interest is on emergent phenomena in quantum matter. So obviously, when I prepared the classes, I thought, what's interesting if for someone who is in this field. And I am just curious, can I have a show of hand? Who here works in condensate matter physics? Like the minority of the minority. I just wanted to be sure that this is the case, because probably then you all, or most of you, know a lot more about cold atoms than me. And so what I'm going to try to tell you is how this relates to this area of physics that is condensate matter, and what physics emerge in this field that is related to the experiments in cold atoms. So I have 3 classes, and I thought, what should I talk about? And I came up with this idea. So today I'm going to talk about the past of the field, the first experiments, and actually the basic things that happen. And tomorrow I'll talk what's going on now. And on Friday it's like a futurology exercise, what might come next. So I had a lot of fun thinking what might come next. And it was actually great for me because it made me think, what can happen in this field. So I had fun preparing these classes. So about the past, so this is what I intend to cover today. As I mentioned, the basic things about experiments and theory, so trapped ultra cold atoms. And then I'll jump to optical lattices. I know you had classes with Raul last week, and he said a lot about trapping and cooling, so I won't cover it again. He knows a lot better the subject than me. And then I'll jump into many-body physics within the optical lattice framework. And the 2 topics that are, started this field that are related to condensate matter, which are Mott physics and magnetic states. And I hope I'll give a flavor for you who are not from condensate matter backgrounds, why this is fun and what these things are. And I went talking about the quantum gas microscope, which is, in my point of view, what sets the present of this field. The ability to have in situ imaging with atomic resolution. So all the experiments from this past that I mentioned today, they were like bulk experiments. People measured whatever happened in the trap and in the optical lattice as a whole. And what I'll describe in more detail tomorrow are experiments that are looking into atom-to-atom physics that have come in the past 10 years or so. So 20 years for today, 10 years for tomorrow, and the future for Friday. So trapped ultra-cold atoms are really interesting. I'm not sure if you thought about this very much, but one of the most commonly trapped atoms is lithium. And here I wrote, oh, I have a flag here. So lithium-7 and lithium-6, different isotopes, and they are very similar, and on the other hand, completely different. The similarity is obvious. They are both neutral lithium atoms. I'm only going to talk about neutral atoms here. I've heard, you've heard about ions this week, but I'm not even going to say anything about it. They have the same number of protons, they have the same number of electrons, they have different number of neutrons, which is a neutral particle and should not make much difference. But whenever you have integer spin, that happens here when you have 4 neutrons, it's kind of like the electrons and protons spins counterbalance each other, and whatever number is you're left with for neutrons. If it is an even number, then you have an integer spin, and then you have bosons. This is a boson, and in the case of lithium-6, you have 3 neutrons, and then you have a fermion. And in most of the experiments, lithium-7, rubidium-87, and potassium-39 are the most common bosons trapped and studied. As for the fermions, lithium-6 and potassium-40 are the ones that are more studied, and of course they are as fermionic as an electron, and this is going to come up in a bit. So being a fermion, you have to obey Pauli exclusion principle, and this makes life very different. This is a sketch from the News Focus and Science, a node 1. If you cool down bosons on a trap, what happens is you have the quantum states, and as you're cooling, you're bringing the bosons down, and you have eventually a Bose-Einstein condensate where all or most of the particles are here at the lower level, the lowest level. And when you have fermions, you can't do that, and so you can only have one particle per state, and here I put 2 because I have spin up and spin down, and so these are actually different particles, one with spin up and the other one with spin down, and then I have this Fermi degenerate state that you see here. And as you can guess, these are very different things and behave very differently. So I don't know, I mentioned that the Bose-Einstein condensate was achieved in 95, 30 years ago, and then 4 years later, the degenerate Fermi gas was achieved, and the figure is not nearly as nice as all the condensate, plots and figures we have, but this is how it was achieved. It was in the group of Debbie Jean and Brian Marco took part. We have 2 hyperfine states here, MF 9.5 and 7.5 with the different F 9.5 and 7.5 with the different MFs here. And throughout the talk, I'm going to abuse the language and call spin up a given hyperfine state and spin down another given one. People do this so frequently in this field that they don't even think about this anymore. But this is an abuse of language. These are not spin up and spin down. These are 2 hyperfine states. And you can see here there are many, 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 but we select only 2, so we have up and down. And this is because we want to think about electrons and spin up and spin down. On the last day, I'll talk about SUN, where we increase the symmetry and keep more of the states, and this leads to very interesting and new physics. But this is the degenerate Fermi gas that was achieved a few years after the Bose-Einstein condensate. So in all the experiments dealing with fermions, it's kind of Flamengo and Corinthians. You have the lithium-6 group and the potassium-40 group, and people who work with one really love one, and people who work with the other really love the other, and they don't mix. But to me, I'm Flamengo, but it doesn't matter. So there are people who work with lithium-6, and these are the hyperfine states that we are going to call up and down. And potassium-40 people that use these systems, but the physics is basically the same. To me, who am a theorist, you know, if you're trapping these things, you have different lines and different physics that you have to care about to entrap and put these things on an optical lattice. But to me, that I am doing theory, just the same, spin up and spin down. So that's how fun doing theory is. So as I mentioned, I am a theorist and from condensed matter, and I am interested basically in emergent phenomena. And for emergent phenomena to take place, usually, not always, we need to have interactions. So we want to trap the particles, and we want them to interact. So how do we do that? And to that, I'm going to come back to the Bose-Einstein condensate and give you some numbers. So it was done with rubidium atoms. The temperature was 100-something nanokelvin. It lasted for 15 seconds. It looks very short to me, but you know, lots of things can be done in a lab in 15 seconds. And this is the density of this condensate. So it's a very, very dilute system. And here are some numbers so you have an idea of how dilute this is. So if we think about metals, we have 10 to the 22 to the 10 to the 23 electrons per cubic centimeter at room temperature. If we think of a mole of gas of the standard temperature and pressure, it's 10 to the 19th. So this is 10 order of magnitudes smaller, and 7, and this is compared to the number of carriers in a semiconductor. So this is very, very dilute. So why this is important? Because this is related to the way we control the interactions in the systems. So here is some elastic scattering. So I have two particles, two of these fermionic atoms or bosonic. It doesn't change this way. So one has momentum k, and it's scattered through and goes to a momentum k prime. And so the wave function very far away from the scattering spot has this form, a plane wave that falls with R, and some scattering amplitude. And as you probably have seen in a quantum mechanics course, you do some partial wave decomposition, and you have many, many terms. But as this is all very dilute and very cold, what we are going to do is keep only the first term. So only the S wave term, L equals 0, and consider that K is going to 0. So all that sum ends up being just the S wave scattering length AS. So this simplifies a lot the calculations, and this is something we know. And how do we control interactions then? So we have atoms in two hyperfine states, which once again I am calling up and down. And in the presence of a magnetic field, they experience a Zeeman splitting. They don't have the same energy. The energy of the up and down is separated by the Bohr magneton and the magnetic field B. And here is a sketch of what happens. So if they had the same, the field is 0, these two curves would collapse on top of each other, but they are separated by this delta mu B that's kind of erased here. So this quantity is adjustable because the field is adjustable. You go in the lab and you turn your knob and you change your magnetic field. And what happens is, as you adjust the field, you can raise and lower one of these curves until you reach this resonance. So the state that is here resonates with the energy of the difference. So when this happens, this was actually measured, we can see here the scattering length as a function of magnetic field, and we see one of these resonance here. It increases with B until it diverges, but the fun part of it also can be negative. And when it's negative, it means we have attractive interactions. And this is a very cool experiment also by Debbie Jean, when she had 2 atoms of potassium-40, and she is here ramping the B field in this region, turning attractive interactions. And it looks like here particles are disappearing, and they are disappearing because you no longer have potassium atoms. You have potassium-40 molecules, and so they are not seen here, and after the ramp, they dissolve and appear again. So this is super, super cool. She made a molecule of 2 potassium atoms trapped, okay? And this is doable because you can have either attractive or repulsive. I'm going to talk a lot about repulsive interactions, but here, this is so cool, I had to talk about it. So, and this is like in the very early days, 2003, and this is one of the cool things. And after that, there was enormous experimental activity. So she did the molecule, and then they tried to condensate fermionic molecules that, you know, when you bind 2 fermions together, you have a boson, so very much like a Cooper pair, and then you can condensate there. And then look at fermionic superfluid. When you have imbalance, you have more of one species than of the other, so a lot of things went on. And this is just to give you a flavor of what happens when you have fermions trapped, but my interest is more than having them trapped, is having them trapped and with an optical lattice. So on top of the confining potential, so if you do remember that first plot, I said that sketch, it had a parabolic potential, and I believe Raul mentioned different kinds of trapping potentials. The parabolic is just one possible shape, but on top of that, we have a periodic potential. So how is this done? And I put this flag here because this is very important. These systems, they are isolated from the environment, and this is going to be important later on. So the confining potential can have different shapes. Parabolic was very usual in the early days, and then Gaussian and other shapes. Raul gave a set of classes, so I'm not talking about that. I am talking about the periodic potential. So there are different ways of achieving it. The most common one is using counter-propagating lasers that generate an optical standing wave. So any of you who have done experiments in a basic physics lab, shaking a rope and seeing the formation of a standing wave, that's exactly what this is about. You send the wave in one direction, it comes back, and for certain frequencies, you reach a standing wave. And so it happens that the atoms like to sit on the minima. So you generated a periodic potential with counter-propagating laser, and the lattice constant is half the wavelength of the laser you use. You can also use holographic mask. I'm talking more about this later. And so when you do that, there is an issue of dimensionality. So if you use 2 counter-propagating lasers, here this arrow and this arrow, you have a standing wave in the direction, in this direction, so you kind of have pancakes where your atoms like to sit, and you have this set of pancakes here. If you have a 4 laser as shown here, the atoms sit, you know, in this direction here, so you have this cigar-shaped regions where the atoms sit. But for someone who is doing condensed matter physics, I hope it becomes clear that we want to see confining in all three directions, so a set of six lasers that generate something like that, which is very, very much like a crystalline potential. And this is a very common plot that looks like the eggshell when you buy eggs at the supermarket. The distance here between two minima is half the wavelength of the laser. So in this case, 532 nanometers. And this little blue and red balls are the different particles with spin up and down or hyper, in some hyperfine state different. So this is what happens in these experiments. So I'm talking more about geometry tomorrow, but people are really smart and can use different laser pointed in different directions. So if you, instead of having, you know, 4 lasers in a straight angle, you have angles in 6 in 120, you can generate a triangular lattice. Or if you detune, you can, you know, do amazing things, checkerboard. And here is a honeycomb lattice, which is very much studied in condensed matter because this is the graphene lattice. And they even were able to observe, you know, the density of states and the Dirac cones and everything that comes with graphene. So this is the optical lattice graphene. And also the Kagome lattice, this is done for rubidium, so only for bosons. I'm discussing more about this tomorrow, but there is, you know, the possibility of building up the geometry you wish, you know, with some hard work and different lasers. So the idea then is study many-body physics with ultra-cold atoms and in optical lattices. And so what can we do with that? We can look at quantum phase transitions, quantum magnetism, some exotic types of superconductors, topological matter, synthetic dimension, entanglement. The list is so vast, it's hard to choose and pick what I'm leaving in and what I'm leaving out. But there is an enormous amount of things you can do in condensed matter within this platform. And it's hard to accept this when you first see, but this is exactly the same physics as for strongly correlated materials. So if we think of these 2 species atoms sitting in this eggshell potential, the physics is exactly the same one as, for instance, in this compound. And I'm going to talk some more of compounds like this for people who are not from condensed matter. You don't look at this and recognize, but for me, we look here and we have planes of copper and oxygen, and this is what we call a cuprate. This is a high temperature superconductor, which is one of the materials that puzzles theorists a lot, and because we know it's superconductor, but we don't know why it's superconductor. We don't know what's the glue that make 2 electrons want to interact attractively and condensate. So if we do understand it here, maybe we can understand it better there. And this is why it has attracted so much interest from people like me with a condensed matter theory background. So why, if it is the same physics, why bother, you know, learning all this language and the translation in the beginning was hard? Why doing this with optical lattices and not materials? It is because when we're studying optical lattices, we have an amount of control over the experiments that's absolutely unprecedented for condensed matter physics. So we can control the interaction strength, U, by turning a knob. And this is something in a material. You go to the lab and you cook your material and it has some U value and you don't know, or you find out, and you can't keep changing. And when you want to study quantum phase transitions, for instance, you want to keep increasing the value and see, do you enter a new phase when you increase U? What happens? So having control over the interactions is something, you know, is very desirable to understand the physics, and it's not achievable in condensed matter. And lattice hopping also, so you have this eggshell potential, the atom is in one given minima, and you want to go to the next one, and if the laser amplitude is bigger or smaller, hopping is easier or harder, so you can control this. I've shown how you can control dimensionality and geometry. I have not written here how many atoms you put and take in your lattice, spin and balance. Even disorder, you can use speckle noise to put disorder by hand in your experiment in a controlled way, spin-orbit interaction. So the amount of control we have in these experiments is what drives so much interest. And although the physics is the same physics as in condensed matter, here we have a lot more possibilities because we control much more what goes on. So I'll start describing the most used model, which is the Hubbard model. And this this model was proposed in the 60s by John Hubbard to try to explain magnetism of itinerant solids. And so this is what the model looks like. The Hamiltonian is written down here. It has 3 terms. So the first term is this one here, is the hopping term. I erase a fermion with spin sigma inside J, and I create it inside I. So I take it from here to here, just hopping. And as you can see, the height of this maxima control T. We have, as I mentioned, Pauli exclusion principle, so I cannot have 2 fermions with the same spin on the same minima. I have only 1 level per site, so this is very important. Whenever 2 atoms with different spins meet in a single site, they pay a price U, so n up times n down in each site pays U. And I've written this Hamiltonian in the grand canonical ensemble, and I can put and remove atoms in my system by changing the chemical potential mu. So it's a fairly simple Hamiltonian. And the question is, we have a single band. We are considering only one level per minima, so we are in an S band. We are considering only intersite fermionic interactions. The fermions only interact when they meet on the same site, not long-range interactions. We are considering only nearest neighbor hopping. We are not allowing the fermions to hop further than the nearest neighbor, and we are, for the time being, not going to consider disorder. And the question is it too simple? And the answer is not for optical lattices. So when we think about a material, considering that we have only a single band is an approximation because, you know, if we are considering a d electron, we have 10 electrons. And this is not a single S band. And correlations fall with the distance. They are screened by the electrons in the system and the ions that are in the core, but they are not necessarily local. But here, they are, you know, this is a perfect description of the model. And I am not going to talk about a lot how calculations are usually done because I don't think giving much detail about how you sit, you know, and do your calculations in a computer. But I'm going to mention that this is a simple model. It has 2 terms, but does it have a theoretical solution? Do we know how to solve this? And the answer is more or less. So in 1D, Betty Ansatz gives many information about the system, so we know more or less. And we also have the MRG, which is density matrix renormalization group, which is exact as we control what we keep and what we leave out in our calculations. And in 2D and higher dimensions, the unbiased methods are quantum Monte Carlo. which has a fairly big number of people in the world doing, and numerical linked clustered expansion, which has like half a dozen people doing because it's very complex. But these are the unbiased methods. And I want to discuss a bit the difference about unbiased methods and biased methods, because I think it's really important, and people usually don't think much about it. So when we are using one of these unbiased methods as quantum Monte Carlo or the MRG or exact diagonalization or NLCE, it has a very high computational cost. Calculations take a long time. As when we do some approximation, it's fast. But when you do this kind of calculations and you know what you're leaving out, in the case of Monte Carlo, you're leaving out your statistical errors. So if you do calculations for longer and longer, statistical errors are smaller, and you end up with something that's very close to exact. So you know what you get is what is in the model. And when you do some bias methods, depending on the quality of the model, if you do some very simple mean field approximation, you might find very interesting results that are an artifact of the approximation you use it, but it's not actually the physics of the model. So this is just a word of caution on how to solve your models. So this idea of having optical lattices to study condensed matter physics is quite a changing paradigm, because now we can emulate in the lab the model I want to study. So for years in condensed matter, you had a high TC and you think, what is the minimal model to explain this material? And you put hopping and you put strong correlation. Oh, it's not enough. Let me add next near neighbor hopping. Let me add longer range correlations. Let me add a crystal field. Let me add, and you keep adding things to try to explain the physics of your material. And here is the other way around. I want to study this model, so I'm going to emulate this in the lab. And then I'll study the model I want to study. And why do you want to study a model? Because we cannot solve this model, and we don't know all the physics that is in there. So it's good to have, and this is Feynman's idea, to have a quantum simulator to study another quantum system. So this is what the field of optical lattices with fermions in it is about. It's a quantum simulator to materials and condensed matter physics. So how do we translate, from one thing to the other? So what in condensed matter is the role of the atomic nuclei and the core electrons? What's in there, and the core electrons that stay around the nucleus and then move much is done by the optical lattice. This is what generates the periodic potential. The electrons are replaced by the fermionic atoms, the electron spin by the hyperfine state, and the Coulomb interaction between the electrons is replaced by the interaction between the fermions, controlled by the magnetic field, the Feshbach resonance I've shown. And so electron spins are not spins, they are hyperfine states. And there is another thing that people just use very freely. We talk about charge. So, and I will do that. And it's also an abuse of language, because there is no charge here. The atoms are all neutral. So what's jumping from side to side is not a charged electron, it's a neutral fermion. And this is different, but it's, on the other hand, the same. And I'll come to that later. So what's the physics of the Hubbard model? What's in there? And so we have two terms. One term that has this U. You pay an energy U whenever you have two fermions on the same side, and this tend to localize your system. You increase so much U that you freeze the fermions in different, you don't have them in the same spot because you pay too high an energy. And you have the hopping term that favors itineracy. So you have the competition between these two terms, and this competition leads to metal-insulator transition and magnetic order and a lot of fun. So let me first talk about the Mott transition. So it happens when we have exactly one fermion per site. So here I don't have empty minima, and I don't have minima with 2. I have, a single atom in each of the minima. And when we don't have interactions, I turn off my interactions. What happens here, this is my energy band, and I have it half filled. It's filled until this is the Fermi level. These blue states are filled, and these empty ones are available. And if I want to give a little energy to one of the atoms, I can move it from here to here, and I have a metal. When I turn the interactions on, what happens is this band splits in 2, and I have here what we call a charge gap. This lower band is completely filled, and this upper band is completely empty. And if I want to promote a fermion from this band to the other one, I have to give this amount of energy that's proportional to the charge gap. And this is measurable. So if I calculate or measure, I'll show some examples, the compressibility. I move the chemical potential here. I increase, and this is increasing the number of particles until I reach this region, and then I increase the chemical potential, and the number of particles is not increasing because there is no available state. So whenever I am within a Mott gap, the compressibility goes to 0. And this is something that has been measured in these experiments. So this is the hallmark of what we call the Mott insulator. So when we study condensed matter in basic physics as an undergraduate, we don't hear about the Mott insulator. We hear about the band insulator, which is not as common actually as the Mott insulator. So the band insulator just happens because the band structure is such that you have an empty band and a filled band. Here, what drives this gap here and separates the filled band and the empty band is correlations. So whenever what drives the gap is the correlation, we call this the Mott gap, because Elliott Mott was the first one who described it. So this is one of the first experiments that saw the Mott insulator in fermionic atoms in an optical lattice. And this drawing here is very interesting because this is a sketch, obviously, but it shows that on top of the lattice, we see here the clear and darker fringe, which mean the positions where the atoms can see. It is very, very clear we have a parabolic trap. And this is very different from the picture I showed you before, because here in the center of the trap we have more atoms, and we have a cloud that the density is not homogeneous because of the trap. And so this is different than having a homogeneous system, and this is very harder to model. But anyway, what they have done, they have added a very, very strong U interaction and have split this band in 2 and left only empty single occupation in the lower band and the upper band here empty. So the way they measure this, here they measure the double occupations. So here we can see we have green and blue in one side, green and blue in one side, green and blue in one side. So we have double occupations here in the center of the trap. And as we increase correlations, that's what they are doing this. The double occupation here is 0. So the way it was done in the early days, this is, 2008. Was that it's a bulk measurement. They measure the double occupation, an average number throughout the whole atom lattice. So this is a bulk measure, but anyway, it was able to show that the system entered a Mott state. So just to have some idea of the energy scales here. So in this experiment, this is the wavelength of the laser. The S-wave scattering length is in this range. The lattice potential depth is in this range, where ER is the recoil energy that depends only on, basic physical quantities. The hopping, it was very peculiar to me to see hopping given in hertz or gigahertz. I was used to see this in electron volts, but you just need to multiply this, by h bar, and then you have an energy scale. And usually the correlation is given in units of hopping. So you have a flavor of what the numbers are. And so we can use all these numbers to input here and get, T and U as in the Hubbard model. And just once again, remembering we can have this AS here being positive or negative and having attractive or repulsive interactions. So all these early experiments measured quantities in bulk. But this is one of the, so this is a 2008 experiment that used large U and somewhat large temperature. And 2015, they were able to observe the same Mott state at a lower T by doing something different. So measuring here the compressibility that I mentioned before. So here is the density, and here is the compressibility, and we see that arriving at half filling, which is 1 fermion per site, we see a huge drop in the compressibility, and the drop is easier to see for larger U than for smaller U, but even for smaller U, it's possible to see that. And so the points are the experimental data, and this green area here are quantum Monte Carlo simulation to help figuring out what the temperature is. I'll come to that in a bit. So I'll switch to the high TCs now. And so this is the phase diagram of a given high TC superconductors. They all look very, very similar. This is temperature, this is carrier concentration, and we have different phases here. Oops. So this pink, orange area here is the Mott insulator with antiferromagnetic correlations. This blue dome here is actually the superconducting phase, and it doesn't happen when we are not doped. It happens here at some doping. And this green phase changes from material to material. It can be stripes, it can be charge density waves. But the thing that's very interesting about these compounds is that in condensate matter, we like very much to use band theory, Landau theory of phase transitions, or the BCS theory for superconductivity. But in these materials, none of these works. And this is one of the reasons why we have to resort to all kinds of approaches and simulating this, emulating this with an optical lattice to try to understand these compounds. So here in this antiferromagnetic Mott insulator is when we have 1 atom per site, and the atoms are well organized. So here, blue, red, so they are in this pattern. And this is what happens for this material. And so when we talk about magnetism, so we can have some sort of ferromagnetism, which is when all the spins point in the same direction. We can have antiferromagnetism, which is when we have this arrangement. The total magnetization is 0, but it's organized up, down. And we can have paramagnetism when it's, messy. And this transition from here to here is driven by temperature. There are other possibilities, but these are, the most common. And this is the one that is seen in the high TCs. So what's the long-term ambition of, people in this field? I want to see superconductivity in the optical lattices. This is, the race that has been going on for 10, 20 years. But the intermediate step is observing antiferromagnetism. And let me go back to this plot, because maybe I have not reinforced this. But this is temperature. So the temperature here is higher than here. And cooling the systems is a problem. So it's easier to achieve this region because it has a higher critical temperature than it is to achieve this temperature, which has a much lower critical temperature. So for a while, let's reach the Mott antiferromagnet, and then the Mott state, and then the antiferromagnet, and then we'll look for that. So seeing this state is kind of a step towards reaching the superconductivity. So the bottlenecks to do these are cooling. We need to cool to see the state. Thermometry, I have not mentioned this, but how do we know the temperature in these compounds in optical lattices? This is something that's very different from Bose-Einstein condensates. I've talked to Patricia a bit about that. They know the temperature in a condensate by the number of atoms, and here we don't know the temperature. So I'll talk some about this, but we have to rely on a theory and try to match theory and experiments to use this as a thermometer. And there is also the question of imaging, and which I'll come, this is how I end my talk today, and cloud density. These experiments, when we have a parabolic trap and we have a density that's different in each step of the way, are very hard to figure out what's going on, because we have to average different densities. So just to give you a flavor, in optical lattice experiments, we have the temperatures around a few nanokelvin, 30, 20, it depends on the experiment. And just so you realize how cold this is, if we look at the background radiation in the universe, it's 2.7. So this is a lot colder than, the deep universe. The first time I thought about it, this really struck me, this is really, really cold. And this is kind of a countersense in another way, because I want to reach high temperature superconductivity, and I am doing this with a few nanokelvin, and it's not cold enough yet. So this is very puzzling, but this is the way it is. So let's talk about temperature and cooling. So we have, if we decrease the temperature, we reach the Mott state. We decrease some more, we reach the antiferromagnetic Néel state, and we decrease some more, we get the critical temperature for superconductivity. But we don't know how to measure any of these in these experiments. So there is this interesting review here. I just thought I should add the reference. But what is usually done is in these experiments, as I mentioned early on, they are not connected to the environment. They are completely isolated. So whatever you have in there in the beginning, it's there forever. It's adiabatical. So if I know the entropy at some point, then it's the same entropy forever, because we can expand the cloud or compress the cloud, and this is going to increase and decrease the temperature, but the entropy is going to remain fixed. So, and we know the entropy. The entropy for the Mott insulator is log 2. And now temperature lower and the wave superconductivity lower. So I'm going to talk a bit about entropy now. So this is how the Néel temperature and the entropy are linked together. So this is a calculation of the 3D Hubbard model. this is the interaction strength U, and this is the temperature. And what we did, we calculated the entropy as a function of temperature for each one of these values, and I marked, this is 0.3, and 0.3 entropy is, here in temperature and U. And I kept following these isentropic lines where the entropy is fixed. And we see by this plot here that I need some entropy around 0.3 to increase U and reach an antiferromagnetic state. And also an important information is, as I increase U, the critical temperature increases, and I've stopped here, but it falls as T2, T squared over U. So this is what we call the sweet spot, which is where the temperature is higher. So if you're an experimentalist and you want to look for antiferromagnetism, don't do as in the early experiments as you use a third, because it's way down here and the temperature falls down and it's much harder because it's lower. So this is, the sweet spot, and this is the Néel entropy to reach the system. But one thing, we can try to take advantage of the parabolic trap. And here I show the density rho as a function of radius. So I have a 3D trap, and I'm showing what happens with as I get away from the center. So this is the center of the trap. And as I have different recoil energies, I can see that here, for this given value of the recoil energy, I have in the center of the trap, one atom per site, so I have what we call a Mott core. And if I close my trap more, then the atoms that are in the outer region, they have to move inwards, and then I have, more atoms in the center, and I don't have a Mott core. So the same way I can calculate a density profile, I can calculate an entropy profile, because the entropy is not homogeneous through the lattice. So what happens here is, in this case of the Mott core, in the core of the lattice, I can reach an entropy that's smaller than the Néel entropy, which is really interesting. If I integrate, I have to remember this is integrate in 3D, the entropy in all the trap, I get this 0.65. But if I, change and open and close the lattice, I see that I can have a central region where the entropy is smaller than the Néel entropy in the center of the trap. This is, something that used to be done in the early days to try to take advantage of the fact that the density profile is not constant. So can we do something about it? And when we look here at the spin-spin correlation function, this is what is showing. In this case, it's a lot higher in the center of the trap. So it's really a way of doing this, because we can shuffle entropy around, and at the Mott state, it has a lower entropy, and antiferromagnetic state even lower, because we are entering an ordered state, and then it has lower entropy. So what we do is we push the entropy to the metallic region, and so the amount of energy, of entropy that's going to the metallic phase is allowing for the center to have smaller entropy, and thus achieving the Néel state. So if we do once again this plot, but now with the trapped core, we see that we don't need to be as low as 0.3 entropy to reach this antiferromagnetic core. 0.65 is enough. So this is something that, helps us to, this information that theory can provide to experiments to help reaching antiferromagnetic states. So now I come with how do we measure antiferromagnetic correlations. And the early experiments, once again, were all bulk. So we didn't have what we have now, which is in situ imaging. And this is a very cool experiment from Randy Hewlett's group, which is Bragg scattering. So it's very similar to what is done in X-ray to figure out the magnetic ordering, but here this is a cool plot figure as well. Here is the optical lattice, and you have light coming in, and you observe this light coming out in two different angles. One, which is the Bragg angle, and the other, there's some given diffuse angle. And just one comment, Randy's trap is very complicated. It's not parabolic, it's some compensated optical lattice. And he's done this way so he could achieve more cooling. So it's a Gaussian with an inverted Gaussian, and this is what it looks like. So it's very, very hard to model, because when we are trying to calculate something in this lattice, it's the average. You know, we have different densities in different pieces, and we have to figure out what's the density, and so it was very, very hard to do. But anyway, it was done. So here is what happens. In this direction, we have constructive interference. And in this direction, we have destructive interference. And what is actually measured is something that it's usually calculated within theory for the Hubbard model, which is the magnetic structure factor. So this is this quantity, the spin correlation function, weighted with the wave vector here, Q, and Q here is just antiferromagnetism. So I'm probing whether it's one, up, down, in this constructive pattern. And here is some random. I asked Randy, why this value? And said, this is where the window is in my trap. So this is where he could measure. And this is the dark symbols here are the measured quantities for the constructive, the antiferromagnetism, the open circles here for the destructive pattern. And this is how temperature was measured actually. So these are quantum Monte Carlo calculations for different temperatures, and where they match is the temperature. So we believe the temperature is around 32. This is not Kelvin, this is nanokelvin. I forgot the N. But this, unfortunately, is still 40% above of the Niel temperature. So he was able to see in the experiments an enhancement of the magnetic structure factor, and this is very similar to that sweet spot. We've seen an increase with U and then a decrease that goes with the square over U, and this was measured, but not quite there in antiferromagnetic place yet. So more recent experiments were able to do that, so this was repeated in 2024, so almost 10 years later, and you know they did this sweep here around this temperature, and were able to see basically the same thing, but here, you know, in a much smaller density, it was 0.6, here's 0.2, and we're able to reach the Niel temperature. So it's good to see this achieved. So I'm about to reach the end. So this I'll discuss a lot more tomorrow, but I am going to discuss this very important step that was done first for bosons, which is the quantum gas microscope. And so this is the first image that I have seen of each one of these dots is actually one atom. And I saw this on the March meeting around this year, and they had the film, so it looked like Space Invaders, you know, the game, the atoms hopping to one side and the other. And this was achieved by, this is a CCD camera, a numerical aperture, just optics, and they were able to reach, you know, single site resolved imaging. And this is a really boost in the field. And as usually happens, it was achieved in 2009 for bosons. And, oh, here is more. So now that you see you have space resolved imaging, you can take these shots and look at these pictures and see the MOT insulator here. And just a comment here, we see this circle with what it looks like an empty center, and that's not what's going on. Here, whenever there are two or more atoms in a given site, what happens is they are ejected by the light. So when you see an empty core like that, it means you have more than two atoms in this region, not that it's empty. But this here is the figure of the MOT insulator for bosons. For fermions, things come a little bit later, 2015, and it was like when the monkeys learned how to do something, like 6 groups did at the same time, and the race was on to do cool measurements now that the quantum gas microscope was available. So I'll start tomorrow with that. It was kind of fast. I thought that I was going to take longer, but nobody interrupted me, and I kept talking. So maybe we can have time for questions now. We have plenty of time for questions if you want to. Microphone is on. Okay. This is the exercise of the week.
Thank you, Thereza, for your great lecture. My question is about the typical size of these optical lattices.
The typical sizes, it depends, but 10,000, 100,000 atoms. But as I'll show you tomorrow, it depends very much on the implementation. So on the early days, like the Jordan's experiment I've shown, they put a bunch of atoms in a parabolic trap and the center of the trap. But nowadays, there are different ways of doing this. There is a way to flatten out the center. And so I'll show tomorrow an experiment from Emmanuel Bloch's group. And he has like a ladder with like 8 sides, 16, 8 and 8. And so then it's completely different. So I think pretty much it depends on what you want to do today, because you can either do very large lattices or a very small one with a flat profile, so you don't have these density variations along the lattice so much. But there are different ways to implement, and so from 10 to 10,000 to 110,000, you name it. Okay, you have one here, and then we go there.
Okay, thank you for your lecture. I have a question. Do you know or have you worked with dynamical phase transitions in these systems, or how these systems can be used to study these types of phase transitions?
I am not going to talk about that, but there is a lot of work going on that, both in theory and experiment. So driven system, Floquet engineering, and thermalization. And so there is this whole field of non-equilibrium optical lattices that I am not very familiar with, but I know that is very, very active. I go there for another question.
So thank you for the lecture. And when you were talking about measuring antiferromagnetic correlations, you said that the density was not like Gaussian; it was strain density. So how can you detail more about this? How can you simulate
so
this
let me.
strange one?
So when you have a parabolic, maybe I have it. When you have a parabolic lattice just like that, you have something like in the Jordan's experiment that you have more atoms in the center and less in the border, and you know how the density changes with the distance from the center because it's parabolic, and you can just, actually when you do calculations, what you do, you suppose a parabolic trap, and then it's like the height is changing as you go far away from the center, and you have more atoms in the center. Here, we actually know the shape. It's one Gaussian with the bottom down and another Gaussian with the bottom up. And the frequency of the lasers he used define the width of the Gaussians. But as you can see here, the shape is not a parabola. It's not symmetrical. And it was just very hard to model. So we kind of had to figure out the density in each spot by knowing the profile of the trap. And then on top of that, if you know the density, then you know the correlation function, the magnetic structure factor in that point, and then it's not an average, it's a weighted average with the trap shape as a weight.
Okay, I have another question. That I think 2 slides next, in the graph that you said that the temperature was above the Neal temperature. I think I didn't understand the graph. Can you tell me why? Because the graph has like 0.7.
So we do know the Néel temperature from calculations. So from, let me. So we do know the Néel temperature from calculations. So this is the first slide is for a system without the trap. The second slide is for a system with a parabolic trap, and we can calculate the Néel temperature for a system with Rendis trap, which is going to give something similar to that, but because of the shape of his trap, the sweet spot, let's call it like that, where the Néel temperature is higher, is not on 8, as it's here, between 8 and 9. It's closer to 11 in his trap. But we calculated what's the Néel temperature, and how do we determine the Néel temperature? We calculate the specific heat, and it has a peak at the Néel temperature. So this is not something you can, do in these experiments, get the specific heat, but I can do in calculations. So we know theoretically what is the Néel temperature for, different shapes of trap. It's just, for the homogeneous, and then you adjust knowing the different densities in the different pieces of the trap.
Okay, thank you.
Do we have any other question? Go.
Thank you so much, Thereza. Is it possible to create an optical lattice with any curvature?
So it is, Patricia has done, tomorrow I'll show you some plots, but it has like little faces and, all fun things that can be done with DMD. So with DMD, there are the good, the bad, and the ugly. So you can draw whatever you want to, faces and shapes, but you have less control. So, but you can.
Thank you so much.
Do we have any other question for Thereza? No? Okay, then, we can close the session for
Sure.
this afternoon. So we meet tomorrow.